Hello everyone, I'm Yuki Shirai and today I will talk about our work about motion planning for simultaneously solving contact-rich grasping and locomotion efficiently. Recro robots have shown remarkable success in locomotion tasks. However, recro robots with dexterous manipulation skills are relatively unexplored. In this work, we call these robots as limb robots and we especially focus on free climbing tasks. In order for limb robots to be deployed, a variety of constraints need to be considered. Therefore, motion planning plays a key role in generating physically feasible trajectories. However, motion planning of limb robots is quite challenging. First, motion planning can be very complicated because it has to consider nonlinear constraints. Also, contact constraints involving discrete variables are necessary for free climbing tasks, since it is difficult to identify contact sequences prior to motion planning. As a result, optimization problem becomes computationally intractable MINLP. Another problem arises with patch contacts. With patch contacts with microspines, limb robots can effectively increase friction, which is useful especially for free climbing tasks. However, multi-finger patch contacts with microspines are not discussed yet in previous motion planning works for limb robots. Thus, in this work, we present a motion planning algorithm that can efficiently solve locomotion, grasping, and contact using ADMM. Then we propose a simple contact model for patch contacts with microspines. Our algorithm is validated on a 9.6 kg 4-limb robot with spine grippers for free climbing tasks. Our problem statement is as follows. We consider multi-rectal robots equipped with 2-finger grippers. Each finger makes patch contact with microspines. The environment consists of rigid static convex holds. First, we discuss contact model. We consider that each finger generates 4D wrenches where we have 3D forces and 1D moment acting along the normal vector of the patch. The challenge here is that we don't know how to consider patch contact with microspines. The key insight is that we have two different wrenches which follow different limit surface model. In other words, the frictional force from patch contact and the frictional force from microspines are essentially different, and they follow different physical phenomena. In this work, to easily consider these two forces, we consider the total available wrenches lived in a Minkowski sum of those two models. Next, we discuss our motion planning algorithm. The objective is to design optimal open loop trajectory of finger and body pose, contact wrenches and contacts simultaneously. In this optimization, we consider centroidal dynamics, and for each finger, we consider position kinematics approximated as box. Also, we consider finger orientation kinematics, which is unique to limb robot motion planning problem. We consider contact for each finger using discrete variables. For each wrench, it needs to follow the proposed limit surface model. We have collision avoidance constraints involving discrete variables to avoid collision between the fingers and the climbing holes or obstacles. This optimization framework is already our contribution, but this leads to computationally intractable MINLP. To solve the entire problem efficiently, we propose distributed optimization-based motion planning using ADMM. It consists of 3 steps. First, it solves MIQP involving integer constraints. Then, in the second step, it solves NLP to consider full nonlinear constraints. And in the third step, dual variables are updated. The proposed ADMM converges once those two optimization problems achieve consensus. The advantage of our method is that we can employ the off-the-shelf solvers such as Groby and IPOpt. Also, each subproblem is smaller than the original MINLP problem, so this algorithm is less sensitive to parameters. We propose another option by utilizing the structure of motion planning for limb robots. We can decouple the MIQP with NL problems where NL is the total number of limbs, which can be solved quickly and thus the total computation time would be decreased. We first discuss the computation results. Overall, our method shows better performance compared to the benchmark method. Also, for walking task, 5-block ADMM shows a better result, and for climbing, 2-block ADMM shows a better result. This is because it's more difficult for multi-block ADMM to satisfy consensus for a relatively difficult problem since it has more blocks. These figures show evolution of residual of body rotation and finger forces for free climbing. Overall, we observe that our proposed method could converge with small enough norm of residual. And as we discussed, we verify that 2-block ADMM shows a smaller norm of residual for free climbing tasks. Next, we discuss how the generated trajectory behaves in a real robot. Here we show 2 trajectories obtained from 1 iteration of ADMM and 6 iterations of ADMM. If we use the trajectory from 1 iteration of ADMM, since it does not achieve consensus among these 2 optimization problems, it is physically infeasible in experiments. However, if we use the trajectory obtained from 6 iterations of ADMM, since it achieves a consensus, it generates a physically feasible trajectory and the robot is able to realize climbing. We deploy our robots with obstacles and our planner is able to design collision-free trajectories. If the height of obstacle is not so high, the robot simply gets over the obstacle. If the height of obstacle is high, the robot takes detour to avoid collision. We even verify our methods with varying coefficients of friction. Each climbing hold has high friction phase and the low friction phase. Our planner finds a trajectory that rotates the gripper so that the finger makes contact on the high friction phase. Finally, we discuss the importance of considering patch contact with microspine constraints. To verify this, we have 2 defined trajectories obtained from optimization with and without this constraint. As you can see, with the constraint, the contact does not slip, while without the constraint, the contact does slip. These 2 figures show the time history of measured and reference ranges. With the patch constraint, since the slipping is prevented, low-level force controller could successfully track the reference ranges. In conclusion, we present model-based motion planning for solving contact-rich grasping and locomotion simultaneously and efficiently. Thank you.